Okay, thank you for the introduction. So I work as flight operations lead at UNSW Canberra Space, and so I'm just going to spend, I guess, the next 10 minutes talking a little bit about how we go about that. So our team is based in Canberra, formed in 2014, originally a very small group of 4 that came down from University of Queensland. I was a PhD student at the time, kind of off on the side. A few years later, we're now about 40 people, combination of engineering and research. We've launched 3 satellites and we've got another one planned for launch early next year. Our first satellite was the Buccaneer Risk Mitigation Mission, and that one was a joint project with Defence Science and Technology Group. We launched November 2017, and my first day on the job was actually our launch day, which was a little bit terrifying. That mission went really well. We finished the mission a year later, November 2018. Then went on to the next one. The next one was one that we did solo, which was M1. So that one we launched in 2019. It was, while Buccaneer was mainly commercial off-the-shelf systems. This one, we now had a bunch of in-house design systems that we were going to test out for the first time, kind of as a stepping stone to the next mission. We weren't able to make contact with that one, so it ended up being a very steep learning curve for us that we ended up growing a lot from, but I'll talk about the details of that a little bit more later. Our current mission, which I have done the most work on, is M2 Pathfinder. So that one launched 2 months ago, 13th of June. We'll also talk about that one more later. And we've also got M2, which is scheduled for launch March next year. And that one is very cool. It has a lot of payloads on it. And it is actually 2 satellites. 2 satellites that starts as one. So they start joined. And then after we've commissioned them, we command them to separate, and we end up going to use them as a formation flying demonstration. How do we operate our satellites? So I've got a picture on the left there of, I guess, the kind of typical what people think of when they think of kind of mission control operations center, which is ESA's control center for the Columbus module of the International Space Station. So that one will be a dedicated control center. Everyone's got a dedicated computer that they work at. Also 24/7 staffing. Depending on, I guess, definitely need the 24/7 staffing for the ISS, for example, because you've got astronauts on board. That is kind of a similar setup for a lot of large spacecraft. On the other side, we have our control center, which we don't actually have a control center. So we operate from anywhere with an internet connection. So I don't need a special office to operate. It'll just be whatever my normal computer is. Operate from my laptop, can technically operate from my phone, although it would be a bit of a pain to do that, but technically possible. Also very convenient during COVID lockdowns, that it's not at all a problem to operate from home. We also, with a couple of exceptions, stick to business hours staffing. So we will schedule the operations in advance. We essentially check on the health during business hours, schedule things in such a way that that's safe for the spacecraft, and don't work weekends, don't work nights, don't have a rotating roster. The way we go about that, so we have our own web-based operations software, which we've called Ops Toolkit. We'll use that to put together commands that we want to send to the spacecraft, send that over to the ground station. When the satellite comes into view, it'll send that up to the satellite. We'll get down the responses, and that'll get fed back over into Ops Toolkit. The communications windows are limited. So Pathfinder, for example, 600-kilometer altitude polar orbit. It does 15 laps of the Earth each day. Because the Earth is spinning underneath that, we only see 4 of those orbits a day from Canberra, and it's in view for each of those, in view of our ground station for about 10 minutes each time. So we get about 40 minutes of contact time each day, and so those are the only windows that we get to find out how it's going, to downlink any data that we need. It also means that if you're trying to do anything complex with it, you've got kind of a 12-hour window where you don't know what's happening with the spacecraft, and so you'll schedule accordingly. So for example, if we're doing something that we haven't done before is somewhat higher risk, we'll schedule that to run immediately before the pass so that we can see how it went very soon afterward and respond quickly if we need to. In terms of the mission phases, so before we launch, we have the design phase, the build phase, and the test phase. As an operator, it's important to get involved in the design phase as much as possible, because you tend to notice issues that will affect operations more so than somebody from a design perspective is likely to. Not so much involved in the build phase, heavily involved in the test phase. Once we get to the operations, we kind of break that down into several phases. The first one is the launch and early orbit phase. That one is the most critical phase for the mission, where things are most likely to go wrong. So you'll be launched by whoever your launch provider is. You'll then be ejected approximately once you reach your orbit. And it's then entirely over to you. The spacecraft's on its own. You need to find it. You need to contact it, make sure that it is healthy. Sometimes in that phase, there'll be a lot of automated things happening, like antenna deployments, sometimes solar panel deployments. So it's quite a time critical phase to find your spacecraft, check that it's okay, before you can move on to the next phase. Next one is in-orbit commissioning. At that point, you'll go through and check out all the different subsystems, make sure they're all functioning as expected. Once that's all done, we can go into the main mission. And that's where you'll be ticking off all of your mission goals, the reason that you launched the spacecraft originally. If you're lucky, you'll get some extra funding and you'll have an extended mission phase. Probably people have had a bunch of ideas of other things we could do with the satellite while it's up there, and you'll try and run those in extended mission. And finally, once you've either it's died or you've decided that you've kind of got everything you want to get out of it, then you'll enter a disposal phase where you'll put it in a safe state for re-entry. I wanted to just spend a bit of time going over our experience of LEOP for each of the missions that we've done so far. Buccaneer was an interesting one. So again, this was my first day on the job at the time. So I was kind of watching on, but it was definitely a stressful period. About, I think, a week before launch. So at this point, the spacecraft is integrated with the rocket. You can't touch it if you find any issues. But we discovered that if we didn't make contact within 48 hours, and 48 hours is relatively quick considering all the things you need to do to actually find the spacecraft. So it's not necessarily uncommon for it to take longer than that, particularly when it's your first spacecraft. But if we didn't make contact in 48 hours, some invalid settings would be applied, which is essentially a safety feature that had an issue with it. And if that happened, we'd never be able to talk to it again. So it was, ended up having a lot of rehearsals to try and make sure that we could contact it within that 48 hours. Ended up making contact on the first time it came over DST's ground station. Was able to reset that timer and everything was all good. The spacecraft ended up being fine and we ended up being able to do the full mission. M1 was different again. So M1 launched on, it was Space Flight's SmallSat Express, which were launched with, I think, 64 small satellites in total, mostly from different owners. All spat out somewhat together from the rocket. It took, so generally it'll take up to a few days for each satellite to be catalogued, and then you're given the tracking information that you need to be able to track the spacecraft with your ground station antennas. In this case, it took weeks to identify a huge proportion of them because they were just kind of in a swarm of satellites, and people would talk to their satellite and respond, but they wouldn't really know which one in the swarm that was. And so very slowly over weeks and months, more of them would be identified, and we were still unable to make contact with M1. So at that point, it was particularly hard to debug, because usually, for example, if you're trying to rule out an issue with your ground station, you might try changing one of your parameters, for example, frequency sweeping across a pass, because maybe there's a frequency offset wrong. There's been a frequency drift, which means you're not quite talking to it at the right frequency. But because we had so many satellites that potentially could have been M1, it just made the search space much, much larger than it would have been otherwise. So we kept we kept that process up for months until we got to a point where we thought that we'd eliminated everything that we could, and it was kind of clutching at straws to continue at that point, and we were better off spending our time working on the next mission. It ended up surprisingly very much benefiting us, because it made us really go through all of our processes, all of our software, for example, with a fine-tooth comb to kind of try and find where all the potential weak links were and improve them for next time. So in some ways, it was quite helpful to actually not know what the problem was, because it meant that nobody could kind of say, oh, well, it's not me, it's not this. Everyone kind of had to try and think what it could have been, and we could improve that for next time. We ended up then having the M2 Pathfinder concept born out of that. So we decided that we weren't comfortable kind of going ahead launching M2, which was relatively complex and expensive, without having had M1 where we were going to prove some of the technologies. So we went ahead and got some additional funding to do M2 Pathfinder. So M2 Pathfinder ended up taking less than a year from the concept phase to being ready to launch. At this point, we did a huge amount of testing before launch, particularly anything that we thought could have been the problem with M1 was very heavily tested for M2 Pathfinder. Very, very nervous heading into the launch, because none of us wanted to go through the M1 experience again. And although we knew that we'd really rigorously tested it, it was kind of always at the back of your mind that, you know, what if we miss something? What if we're just really unlucky and something completely out of our control happens? And it was also a little bit different because we were in the COVID lockdown at the time. So rather than all coming in and having kind of a launch celebration, we were all at home. So here we've got our Zoom screenshot when we were watching the launch, which was live streamed from New Zealand. So that was interesting. And I remember my boss, for example, was asking me on launch day, how was I feeling? Was I excited? And I kind of was explaining that I was kind of excited, but I was also trying not to be excited because I needed to be in a headspace where I was ready to go back into troubleshooting mode if we weren't able to make contact. So kind of, I guess, trying to get myself into a resilient mindset if it meant that we did have to go and kind of repeat the process that we went through for M1. So we did launch. Originally, you're given kind of a set of a state vector, so a time and position and velocity that you're expected to be ejected from the launch vehicle, and you use that to go and propagate your ground station passes and know where to point your antennas to talk to the spacecraft. So you're originally given one that is an estimate, so it's not particularly accurate, but you'll update that later. So we launched on the 13th in the afternoon. About almost an hour later, we had confirmed separation from the upper stage. And about half an hour after that, we had our first ground station pass. At this point, we still had the original orbit information. So we were kind of telling ourselves we wouldn't be that worried if we didn't hear from it, because the orbit information was probably inaccurate, but we're going to try anyway. And for all of our passes, we have our customer on the line on the Zoom call. We've got the entire team on the line waiting to hear if we hear from Pathfinder. No responses on the first pass. So kind of, telling everybody not to worry too much. we started getting a little bit more worried because we had a backup communication system on this spacecraft where it kind of sends out signals independently of our ground station that are received by a constellation of other satellites, and it ends up kind of on a cloud where you can download the data on the internet. And so we're keeping an eye out to see when that auto beacon's happening. Nothing from that. And so definitely, at least internally, getting a little bit concerned. Received new orbit information a little bit after that. Again, thought, okay, well, there was a few minutes difference in that. So that would have been enough for us to not hear anything. But again, no response on the next pass. Went to bed. The third ground station pass was 4 in the morning, a very low pass. So we decided to just sleep through that one. Check the result in the morning, still no responses. Finally, again, the fourth pass, we had everyone on Zoom again. Nothing again until almost the end of the pass. And then finally, we had our first beacon response from Pathfinder. So we kind of got, I think it was a 12-minute pass. We got about 10 minutes through the pass, still seeing nothing. And at that point, I was very resigned to the fact that I thought we were going to need to go through and do a repeat of M1, figure out why, what could be wrong, why we can't talk to it. We had more information to go on this time because of all the extensive testing we'd done. And pretty much jumped out of my chair when I finally saw a beacon response. Had to go offline and do some analysis to make sure it was definitely Pathfinder responding to us. It wasn't something else that was talking to us. Someone hadn't left another satellite out near the ground station that was talking to us. But it was Pathfinder. So yeah, since then the mission's going really well. So we finished commissioning and we're a good way through the main mission now. And I think my time is up. Thank you.
So yeah, thank you very much. So sorry, I just have really one quick question because it's something you touched on. How long does it often take to communicate with a satellite? You know, it was funny because you touched on this, right? I've always viewed, and I think some people may, you send it up, it works. How often does it work?
Good question. I mean, so for us, we've only got, we've kind of got all sides. So I mean, Buccaneer, we got it on the first try. M1, absolutely nothing for months. Pathfinder, a couple of passes, we figured out what the issue was later. And for M1, for example, on the same launch, there are still 12 satellites that are unidentified. So yeah, 12 that also weren't able to make contact. In terms of how often, I guess on average, I'm not entirely sure. I think it is quite common to not make contact initially because you do only have estimated information at that point. It also depends how many ground stations you've actually got access to. So if it's a very expensive satellite, you might end up during the LEOP phase, for example, using multiple different ground station sites so that you've got more coverage, so that you are able to make contact more quickly. Whereas if you're kind of, for small satellites, you don't necessarily have the resources for that, or it isn't necessarily justified to go and have that many different ground stations to make contact more quickly.
Yeah, that's quite interesting. I mean, I felt your emotion almost, especially with M2 Pathfinder, like, hey, is it gonna launch? I'm really excited. Oh wait, I gotta get to work so we can track it so it doesn't go wrong. Like, it's this interesting juxtaposition between working and not working, and excited and fear, all in like 10 minutes. So literally, I guess a space roller coaster. So David has asked a question. Is it possible to put a radio beacon on the satellite so you can kind of find it like an EPIRB? So kind of like an EPIRB that is beaking and you can hone in on it. Does something like that exist on a satellite?
It does. So that was essentially what our backup comms system was for. We are still trying to, we did end up getting a beacon from it eventually. It worked for about a day. It turned out that, so that was a commercial off-the-shelf system. You needed your spin rate to be below, I think, 3 degrees per second, and it needs to be pointing kind of at the global star constellation. And it turned out that we had been ejected at a higher tumble rate than we were expecting to, and so it just wasn't able to lock on. And we also seemed to be quite regularly pointing away from the global star network, so it ended up just being, I guess, less reliable than we were expecting. But yes, there's also, we did have an option to actually have our primary communication system doing kind of an auto beacon as well. But you also have the frequency licensing coming into play. So in this case, because of the frequency we're using, we're only allowed to transmit when we're over Australia. And so it would have ended up being quite an added software complexity to kind of have it work out, use GPS to work out when it's over Australia and only auto beacon then and that kind of thing. There are certainly people looking into systems or potentially using systems that do similar things. So yes.
Awesome. Well, again, thank you very much, Courtney. So our next speaker is Johnny. So Johnny is at Maxar. Now, Maxar is the company that's been sponsoring Satellite Selfie and ACT and surrounds in Northern Territory. And I have a surprise for everyone at the end of some previews of Satellite Selfie, which has been fantastic. And so Johnny is the head of sales engineering at Maxar's Asia Pacific. So he kind of connects the consumer, the customer, someone like who Kara and Rohan will be, who will talk to your next speaker, to the technical bit. So that critical person from, I have an idea and I'd like to do something, to, can you actually do that idea? Which was literally me a few months ago when I came up to this idea. Can we do Satellite Selfie? Trying to connect those dots. So Johnny and his team are that integral part of making it happen. So I'll pass it over to Johnny, who can talk about the great work that Maxar is doing.
Thank you, Brad. Thank you, Brad, for the introduction. Lovely to be here, and just wish to do a quick sound and visual check. All okay?
All fine.
Oh, great, thank you. So I'd like to kick off my session with this quote. It often makes me wonder if Socrates is a man of the past or future. Hi, again, I'm Johnny. I manage a team of sales engineering APAC, working off Maxar's APAC HQ in Singapore. Every day I get asked the question, what is the best imagery to use to see our changing planet? And the correct answer to this is, it depends, right? Thousands of satellites, airplanes, helicopters, and drones collect images of our changing planet every day. But to determine which is best, you have to consider what you are doing with that image and which capabilities are most important. We make sense of all these different sensors by benchmarking a few key capabilities: spatial, spectral, temporal resolution, and accuracy. I will go through each of them very briefly. Think of spatial resolution as how far you can zoom in. From here, then you can further identify the direction of the traffic flow, type of vehicles on the road, road markings, building footprints, trees, and vegetation, and all the different classifications of discernible objects captured in the image. For spectral resolution, it is what can be seen at each pixel. By combining different spectral bands, like the one that you see here, red edge, yellow, and coastal, you can potentially group or classify objects or land use based on the different spectral signatures. Thirdly, temporal resolution refers to how far back in time can we look and the currency of the freshest image. In this particular example, the many plots of agricultural land at Luxton, we are able to view as far back as 2016 to look out for yearly changes, kind of like a time machine, if you will. And last but not least, the accuracy, as how close an actual object is to where it is actually represented in an image. Satellites offer the unique benefit of continually imaging our planet as they orbit and capture changes every day, from the famous blue marble image taken by Apollo 17 astronauts in 1972 to this high-resolution image taken of Complex 39 at the Kennedy Space Center, the launch site of the Saturn V rocket that pushed Apollo 17 to the moon. Imagine taking crystal clear images like the one that I've shown just now from a camera traveling at around 24,000 kilometers per hour. As the satellite completes an orbit, the Earth has rotated roughly one time zone beneath it, which maintains image recollection time of between 10:30 a.m. and roughly 1 p.m. local time. That's when the sun, our flash, is the highest in the sky and shadows are minimal. Today, there are more than 2,000 active Earth observation satellites in space orbiting at different altitudes and speeds with sizes ranging from a shoebox to a school bus. Many of those satellites were launched to provide that bird's eye perspective Socrates was in search of. At Maxar, we have 4 active satellites that are currently in orbit, all capable of collecting industry-leading highest resolution satellite imagery of 30 centimeter and 50 centimeter. We have a long-standing history of providing highest resolution Earth observation imagery since 1999 with ICONOS. All this archival of image accessible through our cloud-based platform for view and analysis purposes. Next year, it will be an exciting year as we are launching our Worldview Legion constellation. Worldview Legion will provide the same high resolution, image quality, and geometric accuracy as today's Worldview satellites. They will also triple our overall capacity over high demand areas, ultimately creating the needed capacity that will cater to monitoring related use cases. In the current constellation of Maxar satellites, each satellite maintains a sun-synchronized low Earth orbit close to 700 kilometers above the Earth's surface. They circle the poles once every 90 minutes. Upon completing Worldview Legion constellation launches, Maxar constellation of satellites would then be having a mixed formation of both sun-synchronous and mid-inclination orbit. In this formation, we would have the ability of revisit in the range of 7 to 15 times per day. The Worldview Legion capability opens up a variety of possibilities in monitoring type applications to support time-dominant, mission-critical use cases. Not only that, with the amount of revisit per day, Worldview Legion is going to provide an unmatched imagery availability for the whole suite of applications ranging from mapping, change type analysis, and perhaps other that we have yet to discover. Here is a snapshot of the depth of the image archival we have worldwide. And from here, you can see that we are focused in collecting images over coastal, urban, and areas our customers deem useful to look out for changes. When Legion constellation scheduled to be online in 2021, these stacks of imagery will grow at an even more tremendous speed. It will be interesting to see the progress of 30 centimeter imagery stack, since we would then triple our 30 centimeter collection capability. Let me show you a few examples how we help our customers using Earth intelligence. In the D&I world, most defense and intelligence agencies are responsible for producing foundational geo-int across broad areas by cataloging natural and human-made features such as terrain, lines of communication, civil and military facilities, and critical infrastructures. This mission enables agencies to publish maps, manage GIS databases, and to develop a holistic understanding of civil and military capabilities for the purposes of advising policymakers on planning and executing security missions. Focus intelligence requires imagery which is updated frequently, and to be able to plan and collect imagery in a highly prioritized mode. In this example, the image captured enables user to assess the area of high interest. Through discerning the border situation, user can therefore form action plans to set up on-site command posts for on-the-ground monitoring with this bird's eye view from the space. Focus intelligence collection requires images that are as high resolution as natively possible to minimize artifacts that might result in false positive or negative detections. The ability to discern objects from the high resolution image helps users to make good analysis and therefore judgment call when deemed necessary. Back in 2015, we fielded a call from a reporter of the Associated Press, which wasn't unusual since we provided imagery to media all the time. However, after talking with the reporter who made the call, we immediately know the story is different than the usual that we have encountered. We understood that the AP journalists were trying to uncover the exploitation of human beings in Southeast Asia fishing industry. Men are tricked into working on these boats, and they are essentially enslaved for decades. They think they're going to get paid, but they are kept at sea, captive on these boats. Commercial boats would rendezvous with slave boats and exchange fish that would eventually end up in the US supermarkets. The exploitation is known by the people whom are investigating this, but they couldn't catch them in the act. These commercial boats are very crafty, and they know they have to leave the territorial waters where they were allowed to operate, and they would turn off all their tracking devices and essentially become invincible in the ocean. Through the leads supplied from the ground, we have estimated areas of the potential rendezvous points to go after. But it is still a very large ocean to look for tiny targets of such. In this case, we had to rely on our Worldview 3 to collect the highest resolution of 30 centimeter imagery, and we got lucky. We managed to get a great looking imagery after several tries to catch the transshipment in action. With the collected imagery, the Associated Press had indisputable evidence of human trafficking in action by locating and identifying slave-carrying fishing vessels. Monitoring or even preventing IUU fishing is incredibly difficult, as the ocean is vast and largely unregulated. Like most activity that occurs on the ocean, transshipment has been hidden from the world. This initiative shines a new light over the horizon, revealing the extent and magnitude of transshipment. Beyond 2021, D&I use cases that requires low latency for mission-critical, time-sensitive applications. Worldview Legion is going to address this with the satellite access opportunity from sunup to sundown to capture the needed imagery over a highly prioritized area. With the potential capacity tripled over the high demand areas and 30 centimeter imagery increased by threefold, the improvement to all derivatives ranging from 2D vectors to 3D models going to be really exciting. A dramatic increase in the volume of rich data will require scalable analytics to make sense of it all. Maxar's extensive experience in AI, ML, data science, big data integration, and domain-specific analytics uniquely enables us to accomplish this. A lot has happened in the 45 years since the Blue Marble was taken. Today, our ability to observe, analyze, and monitor our planet is unprecedented. We are no longer in a data-scarce situation, and our computing power has increased heaps and bounds as compared to a decade ago. With all this technological advancement, tools, and big data at our fingertips, I believe we are now in the best possible era to garner the insights from Earth intelligence to build our world a better place. Before I end, I would like to take this opportunity to bring up that Maxar is currently running a spatial challenge inviting all brilliant minds to address some of the key challenges in Australia. Training and data will be provided, and the participants will have over 6 weeks to work on their solutions. Winners will receive attractive prizes values more than 30,000, ranging from cash to archive imagery to internship, research, and support. So if you want to find out more, just visit the Maxar Spatial Challenge page, or just Google Maxar Spatial Challenge and you won't miss it. Registration deadline is August 21st. Thank you.
Thank you very much, Johnny. That was great. I to be honest, the human trafficking, that's amazing isn't the right word. It's powerful, right? That it's more than just fun things above us. They're literally, affecting it. And it's one of those end cases or uses that you just would never think about, at least me. And I work on some of these things, it's amazing to see what you can do with some of this capability. I
totally agree, Brad. I mean, this is just a tip of the iceberg. And I think with the more imagery and the kind of frequent revisit that we are going to have, it just opens up the new horizon for us to be able to access to this kind of information in a very timely manner.
That's right.
That proves to say that, this is going to be a data-rich era where every single user will have the chance to access to the data when they need it and where they need it.
Yeah, I agree. We have a question from Kylie who's asked, with so many satellites going up, who manages air traffic control? Is like traffic congestion an issue?
I believe before launch, we would, as a commercial company for US, we would actually go through the appropriate authority to ensure that appropriate license and window is secure, and more importantly, to be able to secure the right area the time of the launches to reach the altitude that we want. So all is depending on the incumbent government that actually the company is actually residing.
Okay, interesting. Yeah. And maybe at the end we'll have Courtney's input as well. Well, thank you very much, Johnny. We'll have again more time for questions at the end, and we'll sum it up there. I'm going to pass it on to Cara. And so Cara is based at Charles Darwin University, though she's in Victoria for earthly reasons, let's say that. Look, I think it's really cool using like GPS to actually track brush-tailed possums at night. Like, this is kind of amazing. Also, that is the coolest intro. I love it. What more could I say? I'm going to pass it on to Cara.
Thanks, Brad. So I'm a PhD student at Charles Darwin University, and broadly my research focuses on tree-dwelling mammals and looking at their tree hollow ecology and hollow availability in tropical savannas. But tonight I'm going to share with you a bit of a trial that I've been doing, is using everyday GPS travel trackers to investigate where northern brush-tailed possums go. So firstly, I would like to acknowledge the Larrakia people, of whose country I usually work on when I'm in Darwin, and also the Gunai people, where I'm currently living and working and presenting from tonight, and also the Tiwi people, whose country this research is being conducted on. I'd like to pay my respects to their elders past and present, and also acknowledge the other organisations and funding bodies that help make this research happen. So you've probably seen a brush-tailed possum before, and if you live in the Darwin region, you've seen northern brush-tailed possums pretty commonly in the urban areas, but out in the bush, they're actually quite rare. And in the suburbs, we know that they live in our roofs, they create drays, which are nests out of twigs. If you've put up a nest box, they might live in those. tree hollows if they can find them, or any other locations like that little possum there at CDU outside the morning tea room. But an important question, knowing that these species are not actually very common out in the bush and don't occur all through the savannah like they should because they've actually been declining, is we need to figure out, well, where do they actually live in the savannah, and what resources do they use, what needs to be there for possums to be able to survive, and how large of an area do they actually use, which is important if we do find some possums out there. How large of this area do we potentially need to manage? And so I thought maybe I could use some GPS trackers to help answer these questions. And so I was out on the Tiwi Islands and I was radio tracking a number of different species of tree-dwelling mammals, looking at what types of trees they like to den in. And because possums were large enough, I actually was able to use I Got You trackers, which are just everyday trackers that you can buy, and modified them to put radio trackers on so that I could actually track the possums at nighttime without having to be up 24 hours a day. And then I would send them out with their little backpacks on, and I programmed these trackers to only operate between 6 p.m. and 6 a.m. when the possums were active. And so I could actually see how far they were moving away from the trees that I was finding them in during the day. So what's really great about these trackers is that you can buy them online yourself. In fact, I trialed them on people's pet dogs before I put them on the possums to make sure that they actually work. And this is the interface that you get when you use the system that comes with the I Got Yous. And you can see an S and an E for the start and the end. And that's one possum's movement over one night. And so you can see that, you know, you could use this to monitor where you went hiking or where your dog goes if you've got a large property. But that interface wasn't particularly useful for how I wanted to use the data. So I was able to extract it and I put it in a good old Excel spreadsheet. And one of the first steps that's really important is that I have to clean the data, and I actually have to remove any data points that don't have a sufficient number of satellites. So you can see that's why my first number is actually number 9, because the first bunch actually didn't have enough satellites to get a effective latitude and longitude. And then once I've cleaned out this data, I can actually start looking at the movement of an individual. So here is a possum who was named Capskin, and this is his movement over the course of a month. And what you can see is that there's a brief movement going outwards, and then he kind of slows down, and then you'll see another burst of movement. And then we have another day. And so it's a reflection of being at the den tree, taking some movement away, then he kind of slows down and picks up the pace. And we see this movement being repeated and repeated. And what's also really interesting is you can see the scale down at the bottom, and it's 1 kilometre. And so effectively this possum is moving over the course of a month within a hectare, which is about half the size of an AFL footy field. So it's not really a very large area that this possum is actually utilising. And so there's other things that we can do with this data, is that this is just some behind the code to create a contour map. And so like you see a contour on a topography map of the contours going, meaning that it's higher above sea level, as this contours moves in, this is the most concentrated activity that's being shown by this possum. So that inside contour is where that individual spent 50% of his time over the course of a month. You can see that it then moves outwards, and that there's actually a little second island that's 75%. So that's where one of his den trees were, but it wasn't in a significant rotation. So he wasn't using that as much. And yeah, you can see that the 98% is overall that he's using quite a small area, and his 50% of his core range is half of that hectare. So he's really focusing on that area. And that means that all of the resources that he needs in terms of shelter, of trees, of food, and even his ability to socially interact and potentially create baby possums, all needs to occur within this area for these species to continue to survive. So I was also radio tracking these animals at the time, and what really came up is whilst I was going to these areas during the day was that core range really reflects where all of those den trees are. And on average, they have about 5 den trees that they use within 2 weeks. So they need quite a number of large trees that are going to be in that small area, and that they significantly rely on them and they go back to them consistently. And overall, that the area that they're using is not very large. And those movements that are happening in this area are really reflecting the small amounts of movement that they're going across the floor. And then the slowing down is when they're foraging and eating the food, and they're potentially climbing into the trees and having the flowers and the fruits. But yeah, it's really interesting to see that they're not moving very far away from where we would see them sleeping during the day. So what does this really mean in terms of, you know, the context of looking at declining species and the big wide bush is that, well, we now can have a bit of an understanding that they use a very small home range, which means that they could be vulnerable to disturbances, which are very frequent in Northern Australia. So they could be vulnerable to high intensity fires and cyclones. If anyone's from Darwin, a couple of years ago we had Cyclone Marcus come through and remove a heap of trees through the Darwin area. And those are their homes, and the large trees are the ones that support the large hollows. And so they're important shelter. And, you know, when we're looking at small areas, if we're seeing very large fire scars in the landscape, that's very problematic for animals such as these, because they're using quite a small area, and if that all gets burnt, what are they going to eat? Where are they going to live? And it tells us that large trees and flowering and fruiting shrubs are really important. So for managers out in Northern Australia, there's a lot of prescribed burning or burning for carbon credits. And so we need to actually start thinking about, on that macro scale, is everything that needs to be here there for the possums to ensure that they have the adequate support and resources to survive. And yeah, that's all from me. And that's my Twitter and email if anyone wants to hit me up. And I do, yeah, lots of work on tree hollows up in Northern Australia.
So that's really cool. Like, I'm sorry, the little animation of like the possum running around crazy, like I felt like my kindred spirit running manically and then stopping. So, I mean, obviously this seems quite, not to put it quite bluntly, useful for tracking these sorts of things. Where's kind of the scope, I guess, is the right way of saying it, you know, is there a balance where we think there's a different type of species that, you know, you can extend this to that would really revolutionize some of the information we're getting that's already really hard to struggle? That's a very open-ended question, I know, but, you know, it seems like there's a lot of cool potential there. Is there like something that's almost the holy grail of animal tracking or species tracking?
Well, I think what's exciting is that now that we're seeing technologies develop is that smaller species are definitely oversighted, and even to get a tracker on a brush-tailed possum, which is one of the largest small mammals that we have in Australia, you know, is still quite a considerable effort. You know, a lot of tracking is done on carnivores and elephants, and the technology's been there for that. And now we're getting to a stage where we can put little trackers on tiny finches, which is amazing. And, you know, they're often species that we don't really know much about. And even, I know something as common as a brush-tailed possum, you know, we've done heaps of research on them, but this species, the northern brush-tailed possum, there's been hardly any studies on them. And so to actually understand where species go and their movement really has significant implications when we're trying to actually understand the resources that they use and the area that they utilize, because we have such a vast landscape in Northern Australia, and it all comes under different management. And so, yeah, it's really important to actually get this movement ecology, because if we don't understand how animals move, we don't understand how they survive and they get the resources and they reproduce. So, yeah, it's all really important.
Yeah, I really like your point, right? It almost in a place is like gigantic as Australia, super critical, right? It makes sense. If you need it to track and help us, we probably need it for our animal brethren, right? So no, that's awesome. Thank you very much, Cara. And I'll hand it over to the last speaker, Rohan Fisher, who is going to talk about resource management with satellites, from indigenous land management and reduction in burning and bushfire monitoring. I think it's going to be, I'm really looking forward to this, to be honest, and very topical. And I'm going to stop there and hand it over to Rohan.
Fantastic. I assume you can see my screen now. There we go.
We can see and hear you.
Okay, thanks, Brad. Okay, so I work Charles Darwin University at the Darwin Centre for Bushfires Research, and the majority of my work is using satellite imagery to map and monitor fires across Northern Australia to facilitate some of the world's best fire management. Just before I talk more about that, I want to just reflect on the fact that satellite imagery really has fundamentally changed our understanding of fire in Northern Australia. So if we look back to 1996, in the State of Environment report, then there was this map that suggested that the vast majority of fires occurred in this tiny part of southeastern Australia. What this map is really representing is where fire scientists lived and what they saw when they went out on there to do their field work. Once we had satellite-based empirical evidence of fire spread across Australia and fire frequency, that map was actually inverted, turned on its head. So this map is of fires of over 18 years, 1988 to 2015, with areas of high fire frequency, so multiple fires over that time, showing in yellow and red, and areas with only been single fire events or showing in green. So we can see that the vast majority of fires occur in Northern Australia. Around a quarter of Northern Australia burns every year, whilst in Southern Australia it's less than 1%. I mean, of course, the fires can be quite bad in Southern Australia, as we saw over the last summer, but most fire-prone landscapes in the north. So this is just a fantastic example of how satellite imagery has fundamentally changed our understanding of the ecology in Australia. The reason we have so many fires in Northern Australia is that the tropical savannas are some of the most fire-prone landscapes in the world. This is because we have very intense wet seasons, which produce very huge grass growth, followed by very long, hot, dry seasons. And then going up into the build-up into the wet season again, we get lightning strikes that will inevitably ignite those landscapes. However, there has been fire management, very sophisticated fire management for the last 60 to 70,000 years across most of these landscapes, using quite sophisticated landscape management knowledge for hunting, for travelling, for ceremony, for farming. So these are highly managed landscapes. However, over the last 30 years, I guess, Indigenous land managers were expressing concerns to Northern Australian scientists, seeing less active management in the landscape and wanting to try and improve the fire management again and return to some of the traditional fire management activities. So around 2002, we developed the first sort of national fire monitoring website called NAFI, or North Australia Fire Information. And this was the first website to actually regularly map and monitor fires across the north. So this is the NAFI interface, and it provides two critical types of fire information supporting natural resource management and rural industries across most of Australia now. The first of these are hotspots. So there are around 5 different satellites that have thermal imaging capability that are constantly sending down information of where active fires are in the landscape. So this is updated every 3 to 6 hours. And it's critically important for that near real-time monitoring of active fires and supports intervention and firefighting. The other information we provide is burn area mapping. So this is critical for monitoring fuel loads across the vast landscapes of Northern Australia and helps with ongoing strategic fuel reduction burning. So this mapping is updated 1 to 2 times a week, depending on what's happening in the landscape. To do that mapping, we're using a satellite called MODIS. It's a moderate resolution satellite. The critical thing about MODIS, it has a very high overpass rate, so we can get 2 images of most of the whole of Australia every single day. So the graphic above is the interface of where we download the images. They're already subdivided into Western Australia, Northern Territory, Queensland and the Kimberley. We download these and are able to quickly map fires at a fairly good resolution. Currently, NAFI covers around 70% of Australia, so all of the northern savannas and most of the rangelands. Although it's unable to map very small fires, because what we're interested in is mapping very large areas regularly as opposed to small fires occasionally. For example, if we look at the NAFI interface, we can see a fire front here, which is highlighted in these hotspots, these stars showing where there are active fires, the green area that are showing areas that are already burnt. If we look at the same fire using a high resolution satellite, this is a Sentinel-2 image, we can actually see that fire front. So there are these other sources of satellites you can use to actually do that higher resolution monitoring, but this is not our focus for NAFI. There are also other satellites that have a much more frequent image capture rate. So this is the Himawari satellite. It's actually a geostationary weather satellite, and it has image updates every 10 minutes. So what we're seeing here is the progression of a fire from a couple of weeks ago over the North Kimberley. And we can see how it flares up each night, goes out a bit during the day, and flares up again in the morning. So really good for that monitoring where a fire is every 10 minutes, but not so good for that high resolution mapping of fire fronts. So NAFI provides not only the map viewer, but also a range of data querying visualization tools derived from the satellite imagery. So you can animate the hotspots to look at the progression of a fire. There's also a range of data analysis tools. We have a very long history of fire information, so you can start to do some really sophisticated analysis of the fire regimes. One thing that is really key to what we're trying to achieve with this work is to improve the type of fire management in Northern Australia, and that's to promote what we call cool burns. So this image is an example of a cool burn early in the dry season, not long after the wet season, when everything's still a little bit green. We can put fires through the landscape that are basically just taking out the grass fuel loads. And they're generally small fires, and all the possums and other animals have plenty of time to escape. And we're trying to avoid very hot late dry season fires like this one. These hot late dry season fires also can contribute significantly to the amount of greenhouse gas emissions in Australia. So by burning early in the dry season, we reduce the nitrous oxide and methane greenhouse gas releases from the really hot wildfires. And by reducing those carbon emissions, and we're able to monitor that through the North Australia Fire Information website, NAFI, we've been able to support the development of a carbon farming industry. So the savanna burning carbon farming industry is now a $15 to $20 million a year industry across Northern Australia. And it's the satellite imagery that monitors and maps those fires is critical to underpinning that. And this is largely led by Indigenous land managers on an Indigenous estate. So a really fantastic innovation being led by Northern Australia there. This is just an animation across the top end of Northern Australia of satellite-derived hotspots. This is from last year. You can see Kakadu in the middle there, putting in some very early dry season burning. It slowly ramps up through May and then going into June, which is now across Arnhem Land. We can see lots and lots of small fires scattered throughout the landscape, reducing the fuel. Now August, September, October, November, we're starting to get some of those late, hot, dry season fires. So you can see they're still occurring through the landscape, but they're largely pulled up by these the mosaic burns earlier in the year. And that's really what we're focusing on, what we're trying to achieve. If we have a look at this graphic, this is another satellite image derived data set from NAFI. And what I've done here is I've compared the frequency of fires between 2000 and 2006 Before, there was a lot of people going back out into country for their active fire management for those early dry season burns, those cool burns, compared to the last 7 years, 2013 and 2019, when there's been more active management. And all the green areas on this map is where there has been less fire compared to those 2 time periods. And that equals to about 340,000 square kilometres where there has been a reduced fire frequency. That's despite the fact that due to climate change, fire weather conditions are becoming more extreme in Northern Australia. In Northern Australia, we've managed to reduce the amount of total fire. So it's a really globally significant success story, using a combination of traditional burning knowledge, new tools and techniques, satellite imagery, and new science, and bringing them all together. I just wanted to mention as well, the NAFI has been around, as I said, since 2002, as an underpin the development of the new regimes of fire management and the new industry. And everyone across Northern Australia involved in land management refers to NAFI, and its usage has also gone up exponentially. So if we look in 2019, we had about 10 million map views of everybody sort of starting to converge on NAFI as the premier source of fire information. So what started small has become really an important web resource. So I suggest everyone go and have a look at firenorth.org, also known as NAFI, and you too can start monitoring fires throughout Northern Australia throughout the fire year. Thank you very much.
No, thank you. I just have to say, like that first graphic you showed, right, of 1995, I think it was, to 2015, changing the fire season. Yeah, it was quite interesting to see how the satellite data just changed observational bias, right? Because that's kind of what it was.
That's right. We didn't have it just a little bit wrong. We had it 100% wrong.
Like, I mean, you're right. It was inverted. Like, I mean, it wasn't even, we missed a few areas. So obviously quite a powerful tool. So we have a few minutes to talk to everyone. So if you have any questions, obviously, please submit them and send them through. So if all our panelists could just unmute themselves and we can ask them evenly to everyone. I guess one question I had, and this is kind of, again, to everyone, all of you have touched on, I guess, different aspects of this. And I think for me, it's been quite enlightening, successful. In your respective areas and fields, what's on the horizon in the next 5 to 10 years? What gets you excited, or what do you think is powerful or people should know that is going to be happening in these areas that, is going to transform the way we do some of the things, as you've all have shown this night? So a very open-ended question, but it's a very open-ended topic. So maybe we'll go rightwards in my screen. Rohan, I'll point to you, and we'll go from there.
Yeah, so I think what's always excited me with satellite imagery is how we can continue to decentralize access to these tools. For me, the utility of satellite imagery is really amplified when it links with local knowledge and understand, particularly in natural resource management, it's a very complicated process that requires a sophisticated understanding of your local place. Satellite imagery can support that, but it's only when they're joined together. So when the satellite imagery gets out of the lab and onto the ground, that people can access and use it and incorporate it into their day-to-day work processes.
Oh, that's great. Cara?
I guess for me, going back onto the developing with GPS and the trackers to actually put them on smaller animals is that, I guess from my perspective, we really don't know as much as we think we do about even our own animals in Australia. In fact, only very recently have we discovered that the so-called sugar glider in Northern Australia is its own species. It's a savanna glider. That's happened this year. And so actually understanding our species is still really lacking, and it's really exciting to be able to use GPSs, have access to them, have them at cheaper prices as the technology develops, and combine that with satellite data to look at the fire scars, to actually look at the productivity in the areas and really start to understand how these animals use the landscape, so that we can keep these species around, which are still very culturally important. And also, for our biodiversity, like to keep that intact. I think COVID this year, it's incredibly important to understand how animals move, where they move, how we interact with them. So yeah, I think it's very exciting, the potential, to keep going forwards and really understanding how connected the world is.
No, it's great. Yeah. Johnny?
Thanks, Brad. I think we have a lot to be excited about for the next 5 to 10 years. I mean, immediately, if you look at beyond 2021 with Maxar's capability of Legion constellation, we're going to see a whole type of different availability of content, and not just availability of content, but in 30 centimeter high resolution. And with that kind of content, that it opens up a door of all kinds of possibility, from vectors generation from mapping to vectors generation to 3D modeling. It's really unprecedented. And for the fact that we have all this data that's rushing to the hands of the user, now it's even more than ever that you need to rely on high computing power or cloud computing to be able to quickly run those analysis on the fly and maximizing the imageries that you collected, because those are huge stacks, and we are talking biggest data ever, right? Biggest data ever that you can ever imagine. Petabytes of data availability at your fingertips to access and do analysis, and those are really exciting. I mean, from Earth intelligence part, I mean, Maxar point of view, this really is exciting moments where we actually start to see where we're going to go into an era where highest resolution imagery is not something of privilege anymore. Now, on the other hand, in the space economy, because Maxar has two main components. One is the space infrastructure, and the other one, which is I've been working for the past 11 years, Earth intelligence. Now, in the space infrastructure front, if you follow our Maxar blog and just type in NASA, there has been a lot of collaboration with the commercial space segment. And a few of those I would like to mention is that in the NASA's Artemis program, it is actually trying to return human to moon by 2024 in a sustainable manner. So from the space infrastructure team, we are actually building those kind of infrastructure that enables this type of program to move forward. And not only that, they're even talking about building robotic arms in space that would actually do refilling for satellite, because we all know that once you launch a satellite into orbit, there's no chance at all for you to refill. Even though it's a well-working satellite on orbit, without fill, it's just not going to do anything, right? And you're just leaving it to decay. So with that kind of invention and that kind of roadmap, we are seeing more and more possibilities in terms of space tech, space economy, and space-related technology. It is exciting.
Great. And Courtney?
I'm excited to see Australia finally getting involved in the kind of big science projects. We've now got the space agencies investing in Australian companies supporting the NASA Moon to Mars project. A few years ago, I mean, when I started my PhD, I had assumed that I finish and then I need to go overseas to work in the space industry. And that was 6 years ago when I started that, and it's the landscape has totally changed since then, and I'm really looking forward to see what opportunities are available and being able to keep a lot of our talent in Australia rather than having to go overseas to work on those projects.
Yeah, I mean, that's a good point, and it's actually something kind of you all touched on is a lot of this stuff is just now accessible and doable. And that maybe wasn't the case 5 to 10 years ago, or even maybe a few years ago. And I think, from hearing all of you, that's one of the exciting things is in all of the diverse areas that you're really specializing in, it's becoming more readily available, and it's just growing from here. And obviously, as Ronan and Cara touched on, and Johnny, you showed, changing the way we just are knowing and discovering things. And I think that's kind of a really cool idea up there. And this relates to a question we had, and and Johnny, this is slightly aimed at you, but it's actually a bit more relevant, I think, for everyone. And that is, so the question is, how is secure is the system? So how can other groups access the data from Maxar that you captured for good purposes? And Johnny, I'd like you to answer that first, but I think it's a bit relevant to, Courtney, and the operations you're doing, and the data and analysis that Rohan and Kara are doing.
I think I'll answer it in the way that I presented it. It all depends, right? The kind of security access component, it depends on the kind of need the customers is looking for. Like, people who is in the defense and intelligence community would want their security defined differently from people who want to access openly on data. Now, freely available data is inevitable because we want to be able to allow people have access, freely to enable them to do the necessary good works like what Rohan and Kara, they all been doing. Again, it all depends, I would say.
Okay. And Courtney, with some of the satellites that you talked about, how, obviously not all of it is Earth observations, but is it more communally accessible depending on if it suits your needs, especially in the growing small sat sector?
How do you mean exactly, sorry?
So, I guess depending on, obviously every satellite has a task, right? Do you see the small sat area being something where even with these big observation satellites that data just becomes more readily available to the general audience, whether that's the public, other scientists and engineers? Or do you think it's going to be reserved into just the person who built it and operated it, so to speak?
I really hope that it can be distributed more widely. And I guess a challenge with that is going to be to figure out how to easily share that data and actually make it accessible to people. And I don't think we've got a solution to that yet.
Yeah, I think that's a good point. And I was actually going to ask this to Kara. You have all this data pouring in. How do we share it and make it publicly available to not just what you discover and what we're discovering, but someone who may say, hey, I can kind of use that for a completely different purpose. So I don't know if you have any comments or Ryan, what you're shown with your great database, what other ways do you think people may in the future be able to interact with it, right? Obviously it's great for fires. Great, it's not the right word here. It's useful for understanding, fire management and practice, but there seems to be obviously trickle down effects to just more broadly, ecology and animals as well. Are these things just?
Well, indeed. I mean, as we've shown, it was the satellite-derived data and the long history we were able to produce that spawned this continental-scale carbon abatement industry, which is being run by Indigenous land managers. So that's really what interests me. It's less the satellites and the satellite imagery itself, but what it can facilitate on the ground. And we're actually in a process, my colleagues are working in Botswana at the moment, developing a similar fire management carbon abatement methodology. And we're also working with people in South America, particularly the savanna landscapes of Brazil. And there is a lot of interest in developing a NAFI type web service to underpin their savanna burning applications there. And it's less about, from my perspective, less about how sophisticated the satellite processing is than making sure that it's provided to support those impactful on-ground applications. And that's what I think we've done in the north. I mean, a great thing working in northern Australia is things aren't theoretical, things are very sort of directed to on-ground application. And that's what the scientists in northern Australia have been able to do, how to leverage some of the greatest sort of high-tech stuff that we've got going in space, and how to combine that with local knowledge and local Indigenous knowledge to have these incredible impacts. And so there's a lot of Indigenous rangers across northern Australia now. The first thing they do when they wake up in the morning, they get a cup of tea or a coffee and they sit down and they open up their laptop and they have a look at NAFI at those satellite-derived hotspots. I actually had one guy who worked at Bush, he was telling me a story about an Indigenous colleague of his, and he says, my wife always complains. She says that I'm always with that NAFI lady. you're never at home. He's always on his website looking at NAFI and monitoring those hotspots. So it's really become a deeply ingrained sort of cultural part of landscape management across the north. And I think it's really been one of the fascinating things watching the growth, the use of satellite imagery over the last 30 years is how what was more of a sort of a specialist sort of lab-based enterprise has now become, everyone uses Google Earth imagery. Everyone's used to it, and it's integrated into our lives in so many ways, and that's going to continue to be the way.
Yeah. Oh, that was amazing. I love the story, by the way. That's hilarious. I'm going to ask one final question, and I know we're slightly over time to end it. And again, thank you to all of you. What's just fun about your job, right? You know, we hear the serious stuff. That's great. Like, what's just fun about what you do? Anyone can start. I'll leave it open. The funnest aspect.
For me, the funnest thing is watching people paint the landscape over thousands of square kilometres, usually from helicopter. They're painting it with fire, and I get to watch that each day, and I get to reflect on the amazing work that's being done out on country.
Wow.
Brad, for me, it's the ability for me to actually meet up wonderful people like this group here, doing amazing things, trying to make use of satellite imagery, make use of all these tools and techniques, geospatial knowledge to really make a difference to the world we are living today. I think that's the great experience I'm actually experiencing in this line of work.
Cara, I'm just looking at you because you're in the middle of my icon.
Oh, fair enough. Well, I guess for me, I definitely love being on ground, and yeah, I get to go out bush and interact and catch critters, which is just such a blast. But I guess it's so great to come back and, you know, get that data and use it and integrate it with satellite imagery. You know, ever since I've started being an ecologist, we're always looking at productivity, the topographic wetness, like trying to look at this landscape and figure out how it works and how the animals interact with it. And so yeah, I just love putting all the puzzle pieces together and actually being able to look at that whole landscape and look at the animals in it and to start to get an understanding of what's going on.
Awesome. Sorry, and Courtney, not last necessarily, but you're great to hear. What are your thoughts?
Well, the thing I find most fun is, I think the don't know why I find it fun, but I guess the challenge of trying to solve problems with something that you can't physically access with a really limited data set.
Interesting. Okay.
That's fun.
Yeah, it's the ultimate challenge, right? You can't see it, you can't really deal with it, but you have to solve it, and the problems usually
come up with really creative solutions because you can't access it, and that process is fun.
Awesome. Well, look, I'm going to end it there. Thank you very much to the wonderful four of you. Thank you very much. I've really learned a lot. Again, I don't have to be convinced that it's cool, but I thought it was even cooler now after listening to all four of you. And thank you to all of our attendees. Thanks for listening. Thanks for paying attention. Thanks for asking questions. Thank you for answering the questions. And to wherever you are on the world, since we're covering 3 different time zones, at least with the people on screen right now, have a good evening and take care.
Thank you very much.
Thank you.